Hello and welcome to this GCSE Chemistry video about nanoparticles. We'll start by taking a look at what nanoparticles are and comparing them to coarse particles and fine particles. From there we'll explore surface area to volume ratio and how you calculate it. And we'll finish by focusing in on the properties of nanoparticles and their uses. Nanoscience is the study of materials on the nanoscale, so really small. Specifically, nanoscience is referring to structures that are between 1 and 100 nanometers in size. So nanoscience is the study of nanoparticles, which are particles made up of a few hundred atoms. There are about 100 different types of atoms, and their diameter will vary, but it is taken to be about 1/10 of a nanometer, so 0.1 nanometers. There are many different molecules, so their diameter will vary, but it is generally less than 1 nanometer for small molecules. Nano is often used in the wider world as a prefix to imply something is smaller than normal. However, nano as a prefix actually has a particular scale. It means a billionth of something. And so when considering length, 1 nanometer is a billionth of a meter, or 10 to the minus 9 meters, or we might write 1 times 10 to the minus 9 meters in standard form. There are 3 different types of particles, each with different sizes and different properties as a result. Nanoparticles are smaller in size than fine particles, and fine particles are smaller in size than coarse particles. And so coarse particles are the largest of the 3, and nanoparticles are the smallest of the 3. Coarse particles are often referred to as dust, and these vary in size from 1 times 10 to the minus 5 meters at their largest and 2.5 times 10 to the minus 6 meters at their smallest. And so the largest that they can typically be is 10 micrometers in size. And so they're sometimes referred to as a code of PM10, meaning particulate matter of 10 micrometers in diameter or less. Fine particles vary in size as well, from about 100 nanometers at their smallest to 2,500 nanometers at their largest. So between 2.5 times 10 to the minus 6 meters, or 2.5 micrometers at their largest, and 1 times 10 to the minus 7 meters at their smallest. And they are sometimes referred to by a code for ease of PM 2.5, meaning particulate matter of 2.5 micrometers or less. Nanoparticles, the smallest of the 3, also vary in size between 1 and 100 nanometers, or between 1 times 10 to the minus 7 meters at their largest and 1 times 10 to the minus 9 meters at their smallest. You could be asked to compare the sizes of these particles. How many times larger or smaller would one particle be than another? And to work this out, you take the larger value that you have been given and you divide it by the smaller. And so if you were comparing the largest coarse particle to the largest fine particle, you would take 1 times 10 to the minus 5 meters and you would divide it by 2.5 times 10 to the minus 6 meters. And you would find out that fine particles are 4 times smaller than coarse particles. Or you might be comparing the smallest fine particle to the largest coarse particle. So you would do 1 times 10 to the minus 5 divided by 1 times 10 to the minus 7 to get 100 times smaller. Or you might say 2 orders of magnitude smaller. And so whilst these particles do exist as a range of different sizes, as a good rule of thumb, on average, each of these particles is 100 times bigger than the next smallest of the 3. We know that atoms are the building blocks of matter. They are the smallest unit that makes up everything around us. When lots of atoms come together, they form materials with specific properties known as bulk properties. The melting point of a material, its thermal and electrical conductivity are examples of bulk properties. One metal atom, one atom of copper for instance, cannot conduct electricity. Conductivity is a bulk property, which means it only arises because of the interactions and arrangements of many atoms or molecules or ions together. And so while individual atoms are crucial, it's their collective behaviour that gives materials their bulk properties. Nanoparticles may have properties different from those of the same material in bulk due to their high surface area to volume ratio. For instance, nanoparticles might be more reactive because there are more atoms exposed at the surface. Nanoparticles might be stronger and harder due to their tiny size, leading to fewer defects at the surface of the material. And finally, some nanomaterials conduct electricity better than their bulk forms. The most important property of nanoparticles is their high surface area to volume ratio, and that's the property of how big something's surface area is compared to its volume. And this is something that you need to be able to understand, but also to be able to calculate. And that's what I want to show you here. So if we take a cube whose dimensions are 10 centimetres for all three, we could work out what the volume of this cube is by taking A cubed, where A is the dimension or the length of the edge. And so the volume of this cube would be 10 multiplied by 10 multiplied by 10, which is 1000 centimetres cubed. The surface area for this cube is taken as A squared. That's the area of one of the faces, but we need to multiply this by 6 because there are 6 faces for this cube. So 10 multiplied by 10 multiplied by 6, which is 600 centimetres squared. And the surface area to volume ratio is calculated by taking that surface area and dividing it by the volume. And so we have 600, we need to divide that by 1000, and that gets us an answer of 0.6. And you might be asked to write this as an actual ratio though, so the surface area to volume ratio is 0.6 for the surface area to 1 for the volume. If we considered our original cube to be a fine particle, and then we introduced a nanoparticle, which is of course smaller, the dimensions for this nanoparticle, for my example, are going to be 1 centimetre cubed for each. We can calculate the surface area and the volume in the same way as before. The surface area of one face is 1 multiplied by 1, and then multiplied by 6 because there are 6 faces for this cube. So that gets us a surface area of 6 centimetres squared. The volume of this cube is simply 1 cubed, and so that gets us a volume of 1 cubic centimetre. And so you can see that the nanoparticle has, of course, got a smaller volume and a smaller surface area as well. We can calculate the surface area to volume ratio for this new cube that is representing our nanoparticle in the exact same way as before. The surface area was 6 and the volume was 1, so the surface area to volume ratio is calculated by taking 6 and dividing it by 1, and we get an answer of 6, which then as a ratio is represented as 6 to 1. And this is for the nanoparticle as compared to the original particle, which is representing a fine particle, that had a ratio of 0.6 to 1. And hopefully you can see that as the sides of the cube decrease by a factor of 10, the surface area to volume ratio for the cube increases by a factor of 10. And that tells us that the smaller and smaller we make our cubes, the larger and larger the surface area to volume ratio will be. Nanoparticles have a higher surface area to volume ratio than coarse particles and fine particles do. But it's not immediately obvious just by comparing one nanoparticle with one fine particle. It looks like the surface area is smaller. But what we're saying really is, if we had an equivalent volume of nanoparticles, we would have a higher surface area than we would for that equivalent volume of fine particles. And so the fine particle volume for my cube that I was showing originally was 1000 cubic centimetres. And then the volume for my nanoparticle was 1 cubic centimetre. And so this means that to have an equivalent volume of both types of particle, both cubes, we would need to have 1000 of these smaller cubes. And having got that, we can see that we have got the same volume of cubes of both types of particle. And then knowing that the surface area of the nanoparticle cube was 6 centimeters squared for each particle, now we've got 1,000 of them. That means that the combined surface area of these 1,000 particles is 6,000 square centimeters, as opposed to 600 square centimeters for the original cube that was being our fine particle. So now we've got an equivalent volume of each of these types of cube, and that means that we have a much, much higher surface area for the smaller cubes. Since nanoparticles have a higher surface area to volume ratio than coarse particles or fine particles, we can use smaller quantities of a material and still get the same effect. To illustrate this, let's assume that we needed 1,200 centimeters squared of surface area for a particular use. If we look at our original cubes, each with a surface area of 600 centimeters squared, we would need 2 of them to give us the surface area that we need. And so that is a volume of 2,000 centimeters cubed for our particular substance. To get that same surface area from our smaller cubes, our nanoparticles, we actually would only need 200 of these small cubes, which combined have a 200 centimeter cubed volume, which means we're actually using 10 times less of our material, and we're still providing an equivalent surface area. Those 2 larger cubes have the same surface area as 200 smaller cubes. And so we have the same surface area, which is likely to give us the same effect, but we're using a much smaller quantity of material. On this occasion, 10 times less. Nanoparticles have many different applications. For instance, in medicine, they can be used to deliver drugs to targeted cells, improving the effectiveness of treatments and reduced side effects. They can also be used in imaging to help doctors diagnose diseases more accurately. Nanoparticles can be used in electronics for improved electrical conductivity, enabling the production of smaller, more efficient components. They're also used in cosmetics to improve the texture and absorption for things like moisturizers and foundations. Zinc nanoparticles can be used in sun cream to block harmful rays without the white residue, making them more appealing and comfortable. Silver nanoparticles can be used in deodorants for their antibacterial properties to eliminate odor-causing bacteria. Nanoparticles also make excellent catalysts due to their higher surface area to volume ratio, enabling more reactions to occur at the surface of the material, making chemical reactions happen faster, and so the reaction will be more efficient. Understanding nanoscience helps scientists create innovative solutions to various challenges in fields like medicine, energy, and environmental protection. And so new applications for nanoparticulate materials are an important area of research. You do not need to know specific examples of the uses of nanoparticles beyond the 6 I'm showing here, but you need to be able to consider the advantages or the disadvantages of the use of nanoparticulate material. It could be that you're given extra information to help you to evaluate the use of nanoparticles for a specific purpose. In general, nanoparticles have a higher surface area to volume ratio than the same material in bulk, and so that allows you to use smaller quantities for the same effect. So in other words, less mass is needed of this material compared to normal particle sizes. And these are the big 2 advantages, and I'd encourage you to focus on these in an exam question. Depending on the situation, it might be appropriate to discuss some improvement to the properties, for instance, nanoparticles being stronger or lighter, or enhanced precision of using nanoparticles. These benefits do need to be carefully weighed up against the hazards in an unbiased way. Disadvantages of the uses of nanoparticulate materials stem from the fact that nanotechnology is relatively new, and so there is some uncertainty relating to their use. There are some possible risks that do need exploring in greater depth. For instance, risks to our health, Since these nanoparticles are very, very small, it could be that they could be inhaled and then absorbed in our lungs. Or they could just be absorbed through our skin into our body in a way that coarse particles couldn't. And if so, would they be toxic? These things do need further research. It could also be that they might accumulate in the environment, or there could be other unknown long-term effects that all stem from the fact that nanoparticles are relatively new technology. Okay, that's the end of this video. Thanks for listening.